Hello, everyone. Welcome to the Apidays session on how to deploy containers on Kubernetes platforms using Helm charts. Today, these tools are here with us to making things a whole lot easier compared to the olden times when things worked very differently. In the past, if I wanted to develop a new app and take it to production, I have had to talk to the sysadmin guys and say, hey, I have a new app coming up. And they say, great, come back in 12 weeks. We will rack up the new servers, spin up VMs, and give you access to it. And for a very long time, that was the norm. And it was widely accepted as the cost to business. The project schedules had no choice but to factor these delays as a way to deal with it. Today, we can spin up new infrastructure and deploy applications in a matter of seconds or minutes. So the traditional IT already feels like a bygone era. My name is Sivaraj Lenin. I'm a product manager from Software AG, primarily responsible for the API management products. And a lot of it that we talk today is applicable to delivering any API management platforms with speed and at scale, be it API gateways, service mesh gateways, or the developer portals. Talking about the deployment tools, let's start with the wizard-driven manual installation. Let's understand what was wrong with it, right? All of us would have used it at some point. Installation wizards were doing the job just fine in the past, and in some cases, they still are doing the job fine. But, they always have had two problems. Scale and speed was an issue, right? So if you have to do a large number of installations, many environments, many data centers, the approach wouldn't scale. And again, because it's done manually, it's vulnerable to errors, so error prone. Today, we live in a different world. We rely on infrastructure as code for deploying containers on Kubernetes. In this session, I would like to take you on a journey to talk about why it changed, what contributed to it, and how modern day provisioning makes it a lot easier using containers and Kubernetes. Perhaps let's have a demo of these cool technologies today. 20 years of provisioning. Wow. From hypervisors to hyperscalers. In the past 2 decades, we have slowly made our transition from one end to the another when it comes to where our responsibility and ownership begins, right? It's amazing to observe how the trend did move from virtualization to the cloud native thinking. Here is the obvious timeline in front of you, indicating the rise of a few popular technologies or the practices, right? The introduction of cloud started to change the ways of our thinking and working. And when I say, I'm talking about the capabilities like infrastructure as a service, platform as a service, or a software as a service, right? And then, just around 2013, when the containers came in, and the containerization orchestration technologies came in, they started to speed up the whole cloud native thinking and adoption. And I would like to do a quick rundown of the areas where we had a shift in our mindset, because I believe each of such dimensions contributed to the overall evolution. Firstly, most of the organizations are slowly transitioning off from building monoliths to either microservices, or in some cases where there is a sweet fit, function as a service. We are also transitioning slowly off from maintaining self-hosted software, either to software as a service or serverless applications. Most organizations are now more inclined not to invest anymore in their data structure infrastructure, and they are all taking a cloud-first stance. When it comes to deploying their new applications and gearing up for migrating their current solutions to the on-premise, to the cloud. That's an obvious one. That traditional IT has taught us all enough lessons, and many are already transitioning to DevOps mindset, or some are even ambitiously planning for NoOps. We all know manual provisioning does not help to do things fast in a large estate of IT, and it's knowledge bound. People should know things, and they are error prone as well. And automation has proven to be worth an investment, and its benefits are hugely rewarding. This is my favorite, right? We are also moving away from a large, cumbersome manual step-by-step process, release manual, or run book, or whatever you call in your organization, to a much more of a declarative approach, wherein the developer just describes the desired target state of the application and more like infrastructure as code, and the platform takes care of provisioning the application and maintaining it over the life cycle of the applications, such responsibilities. It's a wonderful, wonderful world, certainly a much better one than where we came from. So from the old ways to the new ways, how did it happen? Let's have a quick look at this evolution from two different perspectives, right? Number one, which areas were most involved due to the shift in the mindset? And number two, what factors contributed to it? I would like to start with the hardware, right? Physical infrastructure, these days it gets questioned as to why should we own a data center? Why can't we move? The infra teams get challenged each day as to what's stopping us from migrating to the cloud. Talking about the software, it's obvious, many things change, and even how we think of it, right? How we design our systems, how we stop building monoliths and start breaking things down into microservices or function as a service, or how we take an API first approach, for example. The next one on the evolution of wheel is the architecture. Different architectural styles focused different objectives, and traditional monoliths were typically layered systems, meaning the front end, business logic, and the DB for persistence at the bottom of the stack. And these layers were often technologically tightly coupled. And there was not much interoperability with other external systems. Modularity was very poor, and each system layer did all the functions without any functional demarcations or boundaries, meaning orders, invoices, accounts, customers, they all served off from the same system. So when you need to scale, you tend to scale them all together as a stack, regardless of whether a particular layer needs scaling or not. You tend to scale everything. And SOA SOA came in, and it focused much more on, let's say, interoperability, and it broke the system down into functions, and that were loosely coupled, and enforced exchanging information should only happen through contracts, etc. Sweet, neat, but it just ends there. And microservices came in, and when it came in, it just took this to a whole new level. This is where or when interoperability met modularity, right? So much focus was given to breaking things down into lowest unit possible, and by definition of microservices, each module does one thing, and that one thing really well, right? With the advent of cloud and the containers, microservices just really shifted gears, and it took off, and it started to focus more on portability, scalability, flexibility, meaning you can describe your application and build it and ship it, and then you can deploy anywhere in the world. Today you would see that I have an application that I want to show you for a demo, and once I build it and ship it, you can literally approach it in any environment. I'm using 5 today, my local machine, plus 4 different cloud providers like Azure, GCP, AWS, and Red Hat, basically. So OpenShift, I mean. So you would see that shortly. Just lost a dimension, the monoliths tend to get over provisioned, and keeping peak volumes in mind. I have done this, you would have done this, because we think, oh, let's plan for the worst, peak volumes, and we tend to over provision things, and it was usually done at a capex investment, right? It did waste a lot of money as the resources remain underutilized over the rest of the year, or off peak, or however you put it, right? But with the modern day techniques, rather than scaling up the entire stack, you have the flexibility to scale only the modules that you need when you have a demand. And so you can just only pay for what you use, right? And more importantly, you pay for it only when you have to use it, so when the demand is high. So it's a much better world, cost efficient one. And the last one is the methodology. And when everything changed around it, the software methodology also changed. We moved from waterfall to agile or scrum or kanban or whatever methodology. Capex started to transition to OPEX. And as for the operations, the DevOps mindset kicked in, and everybody wants automation with not just provisioning, deployment of the solutions using the right deployment tools with CI/CD, etc. Right? So what drove these changes? If you look at it, no surprises there. The list is on the right. It's primarily the cost efficiencies, and then the resource efficiencies, and productivity gains. And the last one is my favorite, which is the ease of use. If a technology is not easy to use, you tend to kind of not adopt to it. So it's very important, the ease of use of any new thing that we introduce. Okay, so I'm just about to demonstrate containers, but before I do, I just like to do a pit stop and reiterate a couple of things. The focus is speed and scale. If you have a small estate, you can take whatever manual approach. It's not going to hurt you much. But if you have a larger estate and a number of technology stack to deal with, and you want speed and scale, you need these systems to demonstrate certain characteristics, and that are listed on the left hand side. For example, modularity, it is how the things are sliced and diced. So you can pack them together, you can scale them on its own, etc. There should be clear boundaries within them. And the other ones are self-describing. If you see scalability, portability, interoperability, flexibility, and ability to replicate in many different places, many environments, or wherever it is. And if you look at it, we have these characteristics to deliver. What's going to help it, right? These three concepts that you see on the right, they are my favorites, right? The virtualization, abstraction, isolation. And if you see, quite often these three concepts are quite heavily applied to solving these problems of speed and scale and delivering these characteristics. I would like to start with the first one, which is virtualization. Simply put, virtualization is the process of creating software-based version of something, right? It can be compute, storage, network, servers, or applications. And trust me, we have all used and been benefited from virtualization at some point, knowingly or unknowingly. We would all have used it. Now, the next one is abstraction, and it's the art of hiding internal complexity of the implementation and surfacing up a easy to use layer, be it a user interface or a REST API. An example I can give is, think of car as an example, right? You have the steering wheel and the gearbox, and that completely hides. They are really easy to use. All of us use it, which much ease, but they hide the implementation of how the whole overall engine works, how it connects with the wheels and creates the torque, momentum, and all that stuff. So abstraction is a really powerful concept. And the last one is isolation, right? We all know what that means, and it can be done at different levels, machine level or process level. And we will see how the containerization technologies take advantage of process level isolation and deliver the benefits to us. And I guess the summary is, you're going to observe these three concepts much more as we try to solve these problems with the modern day techniques. Great. Why don't we have a demo of containers? A world that I often describe as modularity met portability. And what I have today for you is a really simple web application that serves as a static page. And I have used Nginx to serving that static page. And here is the HTML content for you. Yeah, just a few lines of text that I display as Apidays live Paris, and this demo is from Software AG. What I also have got is a simple Docker file that describes this web application. So what is a Docker file? It's nothing but a few lines of code. Just a moment. So yeah, that's a Docker file. So it's nothing but a few lines of code that contains, describes the application, how to build the container. For example, if you see, hey, I'm saying, hey, I would like to run it on a Unix flavor, and I would like to bundle the Nginx with it, copy the files, the index files, and expose the port 80. And I'm also saying, can you just kickstart as you start the container, start the web server. So it's a way to describe the application. With this one file, where I have described the application, it's also available in the repo. Let me just show it for you. So it's put in a repo. It's on GitHub. It's not just for me. It's for the members in the team or anyone in the world, including yourself, who you are seeing. You should be able to see that repo. And what I do today, you should be able to do as I speak as well, because they are publicly available. And that's just a way of doing it, right? Once the code is available, anybody should be able to take it, build it, and deploy it, rather than think about the days where we have to install our own software to be able to set up an application on our machine. How long does that take? We all know that. With containerization, it's a lot more simpler. You can get started in a matter of a few seconds. So I'm just going to give a demo of how that works. So this is my local desktop. So I'm in a particular folder called Apidays demo. And if any developer has to kickstart with it, just do a copy of the repo. So I'm just doing a clone of the repo that I have available. And I'm just going to get into it. And if you see, it's the same set of files that you see, right? That's the index.html, and that's the Docker file. I just got it from the public repo. I didn't have it, right? And I'm going to just now build it because I want to run and see how it works. Right? I'm just telling Docker, hey, Docker, can you just build this app and take and tag it with the name Apidays web app? And you can see it's trying to build the app using the description of the Docker file. So it is trying to come up with the image, an immutable image that you can take it and run anywhere. So at this point, when the image gets built, you can ship it to what we call as a image registry or a repository, and from there on, anybody in the world or anybody in your team or your other arm of the organization can take that image and run it literally on any platform. I'm just going to show. First of all, let me just bring it to the top. So if I say Docker run, so I'm saying, hey, Docker engine, run my image Apidays web app with the name Apidays web app, basically. So all I'm saying is take the image, name the instance as this one, because you can name any number of instances. You can create any number of instances and name them differently. And I'm also saying expose the port 80. So when I kickstart it, the container comes, and when it comes, you would also see that. That's my local host. It wasn't serving any pages. And if the container comes up, you should see the web page getting served. Now, the same container is what I have kind of put it on the OpenShift. For example, if you look at it, it gets served. This is on a public cloud service of OpenShift, basically. Now, I would also show you how easy it is. You remember, if you have to replicate, scale up, hey, set up another server with the same application. How long does it take for us in the old world? Spin up VMs, install the machine. We would have applied automation here. It is much more simpler. You just come here. I have got one pod and I can scale it to 2, 3, whatever it is. It's really that simple of doing this. I'm doing with clicks. You can even do it automatically, or you can even do it on demand. It's such a beautiful world, very easy to replicate the instances of the application. And I would also like to show you, I have got a Fargate service on AWS, and I'm running the same app there. And if you look at it, just to show you, it was here. So you could see that it's the same image that I run. And so the idea is really simple, guys. Once you build it, it's an immutable image that is compatible. It gives you such a portability, so you can deploy it in any environment. So why is it important? We would just see that in a second. So but you get the idea of portability, right? And like I said, you can take the repo what I have, you can follow the same steps that I did, like just clone the repo, build it, and you can run it pretty quickly in a matter of a couple of minutes from your side. Now, what problems do containers solve, right? Let's have a look, right? So in traditional IT, things often broke, and it cost more and was difficult to use, and everything started to fail at some point in time, right? The way we built it, the way we ran it contributed to it, and the environments were different. There were library conflicts between the environments or different applications, and essentially, when you do the root cause analysis, it will be down to 3 things, right? Virtualization, optimization, isolation, right? You try to get the best out of your landscape. By throwing too many things together, you end up with the conflicts because you haven't isolated enough. You just go with isolation mindset. You say, hey, I run applications separately. No 2 applications are run on the same machine. And then you would end up think about the case where you have just a 4 MB or 40 MB Node.js application, right? You do not waste 1 GB of RAM for just the OS to run a 40 MB. And if you have to run multiple instances and multiple different applications, you will have a huge overhead, like 40 MB compared to a gig of the other operating system tools and stuff to run the VM, right? So you try to optimize too much, you get into conflict, and you try to isolate too much, you lose on the cost. There was no ways of winning there. Something was at stake. And you combine that with the number of technologies you had to run, right? It is not just a web app. You will have in a typical enterprise, from messaging to API gateways to databases to queuing technologies, whatnot, right? Combined with the number of environments you had, from developer machines to QA to the different data centers you have in different regions having different hardware, right? Think about it, right? How can we make sure the applications or the huge variety of applications that I have can be run without conflicts across all these environments? How can I have consistency assurances, right? And that challenge started to emerge. And then, if you look at it, how we use the virtual machines in the past, uh, this is how we provision for a long time, and we used virtual machines and hypervisor is if you like an introduction, is what makes the virtualization possible. And it is nothing but a simple piece of software that runs above the physical server or the host. What hypervisors do is that they pool the resources from the physical server and allocate them to the VMs, also called as virtual machines. It manages these resources through the life cycle. And VM is nothing but a software-based compute machine. They run on physical machines, the same hardware. They have their own operating system and applications, and they are independent of each other, even though they run on the same hardware. So the original promise was cost savings, etc. Yes, it did all work at some point in time. It was delivering the promise, but the overhead, think about the overhead. I said, if this application is too small, this is a huge overhead, and multiply it by number of small applications that you have to host in an isolated fashion, you have a huge overhead here. Now, typically two things are the top needs of container world, right? First of all, right, the isolation. How can I make sure these different application stacks can run without conflicts and in a consistent way wherever I run across all these different hardware estates? Number one. Number two, the ops team were started to think, hey, do I really need to know all these technologies? Because each of them has to be provisioned. How you install a database is very different to how you install a messaging service to how you install a gateway. Do I really need to know the steps as to how to start, how to stop, how to install? It feels a lot too much. Can I just have a world where it's just a form of applications? It's a large form where I treat all of them as cattle rather than pets. Knowing the server name, knowing the application, knowing the steps, we treat them like pets. Rather than that, can I just treat them as cattle, like everything be treated the same way? There was a wish for it. So these two changes started to bring in the need for containerization. So the containerization is a beautiful world that delivered those two promises, I would say. And it's an analogy that we borrowed from the shipping world, where the responsibility of the shipping provider is without thinking what is being transported, put them in a box. It can be a refrigerated box, or it need not be a refrigerated box. It's the shipper who needs to know what needs to go into the box. And all I do is take the box, move it from one place to another. And that's what ops guys were expecting. And that's what container is giving. The complexity, the developer puts it into the box. And once you package it as a container, and when they come out of it, when you have to run, they are all just boxes, basically, that needs bin packing and hosted in production. And the applications, they all look almost similar. And they also run without any conflicts because they are all isolated to run in their own spaces, basically. Now, to reiterate, how does that work, right? It's an application packaging mechanism, and a container typically contains only the application code, libraries, scripts, and that's it, right? It's completely packed, bundled, isolated, and very, very efficient. Like I said, you could run it anywhere. It's a packaging mechanism, let's say. And the isolation, how does it make sure that it is not conflicted, is delivered through the isolation of process. They all share the same operating system, but they don't conflict with each other because it's done at two levels. One, the namespaces, right? It is a feature of Unix that allows the containers to have an illusion of I'm having my own operating system, although it is not, right? And that's namespaces. And then the C groups, which helps with sharing the resources and allocating them and metering them. And with these two simple concepts, we have delivered a wonderful promise of containers to all of us, basically. Let's say that, right? How does that compare with VMs, right? Like I said, it's the efficiency. Containers are far more efficient, and they share the same operating system. There is no guest OS there. And you would have seen a layer here as a container engine in most of the web representations. And I personally think it's technically wrong, because the container engine or the Docker daemon's role is just to kickstart the container. And once it kickstarts the container, its responsibility ends there. Then the container directly interacts with the application, and that's pretty much it. The container and the application directly interacts with the operating system, and there is no overhead. And that's why they are performant and very efficient. Summing up, Think of containerization as they deliver portability benefits, and you don't have to treat the different application technology stacks as pets. You can run them all cattle, and you can scale rather than the entire stacks up. You can scale the module that you need and the container that you need. So it's a brilliant world. And the bin packing done its best for achieving cost efficiencies and the resource efficiencies. Now, when your estate grows and when your ecosystem grows, you would see that, hey, it's becoming verbose, too many commands to run for the containers because I kickstart the container. Although I kickstarted, I have a number of commands to run. You may end up into mismanagement problem, and that's where the need for an orchestrator comes in. And I would explain the orchestrator shortly, but before I do that, people ask about Docker Compose. Can it be an alternative? Can we use it? My answer is really simple, right? The Docker command CLI that I run, Docker build and run, they can deal with one container at a time. Docker Compose was introduced to deal with multiple containers, and it also gives you the benefit of infrastructure as code. You can describe the commands you want to do, and you can just feed it to the engine, and it runs. And in my personal opinion, it's a one-sided approach. It works well with the Docker ecosystem. The clustering solution they have is Docker Swarm, and it beautifully works. And when somebody asks as to can I make it work with Kubernetes, yes, you can build bridges and make it work with Docker Compose on Kubernetes, but that's not the most native way of doing it, And the popular choice out there in the market, you might have also heard that it's Kubernetes as we see more adoption that side. Now, how do I deploy things into Kubernetes? Do I run Docker run commands? No, you have two ways of doing it. You describe, like I said, the infrastructure as code as manifest or Kubernetes objects, and either you can run different commands manually, or you can use something more mature like Helm. We will talk about that in a second. So taking a step back, why do we need container orchestration? Again, the answer is speed and scale. When you have number of containers, that makes a small application. Say I have gateway, and if it comprises of 3 different technologies that form a gateway platform, you have 3 different containers to run for one instance. Let's say that, right? And that's common with any application, right? You will have front end, back end, business logic, and if you multiply that with number of different technology stack you have. Again, you would start to see, right, who is going to decide which container is run where, right? I have a pool of 100 nodes, right? Do I decide I run the databases here, I run this? No, somebody has to take care of the scheduling, and somebody has to take care of smartly. That is storage, right? Do you want to babysit and manually allocate the storage, or can I offset that capability? And this is the beauty of the container orchestrator. Such responsibilities can be offset to the platform, and that's what container orchestrator does it for you. And how it does beautifully well. Scheduling and create the necessary ecosystem for your applications to run. And that's the purpose of Kubernetes. And you achieve the same way by describing the different Kubernetes objects, like, hey, I want a load balancer, I want a service endpoint, I want persistent storage, I want different pods to be deployed, etc. So Kubernetes is nothing but a container orchestrator platform, primarily aimed to solve the speed and scale problem. And there are many flavors there. The Docker Swarm, Mesos, the most managed services, pick anything. They all work the same. They are fault tolerant. They can scale on demand. Trust me, they are very, very efficient in terms of resource allocation, etc. Basically. So, and how they do it is, like how we have container as the minimal unit in the container world. You have something called pod. Think of it more like one container in a pod. That's the best practice anyway, right? The pod is the smallest unit of deployment. And when the developer describes as to this is what I want to put in the pod and run it, he also describes, this is how you can health check the pod, and this is how you can do the liveliness check of the pod, etc. And he says how many replicas he wants or how many instances of the pod, and then he feeds it into the engine as this is the desired state. The engine endeavors to constantly check for that, and it tries to keep the current state in line with the desired state. It's a beautiful, beautiful world. And that's where the self-healing mechanism comes in, and the fault tolerance comes in, and Kubernetes delivers it using a concept called what they call as control loop. It constantly, the control loop controls the desired state with the current state and tries to put it into the desired state. Now, like I said, you never have to worry about bin packing problem. Kubernetes does it elegantly out of the box as well. There are different patterns. The industry is mature, and if you start to follow these best practices, like the one I said, the health probe and the liveness probe, I'm not going to walk you through all that, but I'm just giving a hint that they are available. You follow them, you are definitely going to get all the benefits out of the Orchestrator platform as well. So coming to the last topic, what does Helm solve then? Why do we need it? And like I said, that there are different types of Kubernetes objects for software. If you're running just a container that doesn't need any of the other objects, probably you're okay. The complexity is not much, but in a typical enterprise software, you would want a number of containers to run, different pods, different storage mechanisms you need, and you would want to put them on load balancer, and you want to use certain configuration maps or secrets, passwords, sensitive. You would start to see that when you start to put up your an enterprise software into the Kubernetes platform, there are a number of Kubernetes objects to do. And the same problem what we had in the Docker world would arise as to know, do I need to run multiple commands? Can I just describe them and bundle them together? And that's what Helm does it for you. It's nothing but a package manager that tries to bury that complexity. So it puts the responsibility to the developer, say, hey, you take it, pack it, give it to me. And as an ops person, I just want to treat them as cattle, right? I don't want to know there are 20 different Kubernetes objects to be created for this particular application and 40 for the other one. I just want the same way of doing it. And can I use simple commands like Helm install application name or Helm uninstall application name? And that's exactly what it does for you. It gives you the concept of abstraction, of describing your application as charts. And every time you use a chart and release it or instantiate it or deploy it, you call it a release. And you have a place to put all the charts, and it's a repository. It gives so much productivity. And every supplier out there is now trying to give you repo. And if you see, this is SoftReg's repo, and here you have the samples, and you have the Kubernetes deployment charts here. And if you get into that, you have Helm, and you have for a simple standalone installation or a cluster installation, you have the charts available. So what I'm trying to say is, for your custom applications, you would be writing your charts, but for most of the products, the vendors or the suppliers try to make it really easy for you and give you a starting off point to do it. So Helm is a really good way of packaging the Kubernetes applications and run them effectively. So why don't we have a demo of a Helm on Kubernetes? So for the simple web app, I would say I have a folder here called Helm. And if I say Helm create, so I'm just saying, why don't I start from the scratch? So I'm saying Helm create Apidays web app. So I have that already. So let me just get into Helm. So let me just do that. Okay, so you can see that it creates the boilerplate code for you. For example, if I type this, so you could see it describes the values. It has parameterized everything. So the developer has buried all the complexity. He has surfaced up what can be supplied as parameters. And in this case, what you would say, hey, what image you should run, etc. So I'm just going to do that for you here. So if you see it, so I'm just saying I'm in the VI mode. So that's one replica. I just want to, for the demo purposes, I want to instantiate once. I don't want to run Nginx. What I want to run is my image. So let me just replace the value with the image that we built and shipped. Okay, and the tag, I want to give the right tag. That is the version of image that I want to run, and that's pretty much it. The moment I change it, so I can use simple commands like, let me just bring up to the top, just one moment, so that you can see it clearly. So Helm list is the way to see what I have deployed. I have not deployed anything, and you can see, and I'm going to install the web app. So in this case, what I have done is used cloud platform, which is Google Cloud Platform, and it is trying to run in autopilot mode, which means it will automatically scale. It's a beautiful word. You don't have to say a number of nodes to run, etc., etc. It takes care of the Kubernetes platform. And switching back to Kubernetes, so I didn't have any workloads here. Now, if I just refresh, you would see it starts to spin up that, and it will warm up, and it will come across. And similarly, if you see, everything is a cattle, right? I told you, right? You could deploy even enterprise software, however big or different it is. And I have one here for you. I deployed the gateway, software gateway, using the same command. Treat them all as cattle, Helm install gateway. And here you can see I uninstalled once and reinstalled, and it was today. And it is running these different pods. It's running 2 instances of gateway, 3 instances of Elasticsearch and Kibana, etc. So the point really is, it gives you that benefit of doing it beautifully. So getting to the end, let me just summarize. So containers and container orchestration combined with Helm gives you the cost efficiencies and speed at scale. From the time we used to deploy in months, now we are deploying in seconds or milliseconds. And now from the time we built with the mindset that things should never break, let's build robust systems, and it did work until it started to break, right? And we built robust systems. It wasn't sufficient. We moved to resilient architectures where we tried to recover from errors. And then we did follow that for a long time. And then the mentality kicked in. If I can recover from errors, can I detect it? Can I design for failures? Can I build self-healing systems that are anti-fragile? And we live in a world of anti-fragile systems that are becoming the new normal. And so these are really easy technologies and huge benefits. And I would strongly suggest give it a try. It's easy. And the repo that I used today for the demo are available on GitHub. And for Software AG API Gateway, if you want to run it in dev or production, it's on the Software AG's GitHub repository, like I demoed to you. Please feel free to take it and tailor it to your needs to kind of spin up the environments really quickly. And the last, I'm pretty sure you're going to give it a try, and you're going to be successful with it. And you have been a wonderful audience. I wish you all the best with the containers and Kubernetes world. Thank you. Questions?